All right, hi. Let's try this. Okay, so just as if we were in class, here is our chymotrypsin enzyme. Here's going to be our chymotrypsin mechanism. I don't know if you can see. Yeah, the color's coming through a little bit. So I've tried to make oxygen red always. Carbon's going to be black. Nitrogen's going to be blue. And hydrogen bonds are going to be in brown. But they're going to look pretty much black from what you can see. And that's fine. Okay, so in order to understand this enzyme, first I think this is the entertaining way. And by all means, come up with a better way. Yeah. This is not science. This is the science of figuring out how to remember things. All right, so here are our players in the drama. And so I think the best thing to do is to assign each one of these to a person that you know. Who do you know who embodies these characteristics? So first we've got oxygen. Oxygen is a little bit greedy, a little bit selfish, a little bit dangerous. Yeah, I don't know. Bit of a player, maybe. Oxygen is yeah, it always wants something better. Always going after the next thing, never satisfied with what it's got. All right. You got carbon. Carbon just tries to keep everything together. Carbon is maybe a little OCD. It's always got to have exactly 4 bonds, no more than 4 bonds, and that one tendency is going to kind of drive the process here. So yeah, you know somebody who's kind of particular, fine. They can be carbon in your little version of this play. Then down here you got your nitrogen. Now nitrogen I would see as kind of the peacemaker. So nitrogen will take whatever just in order to keep everything running. It's like fine, it basically deals with oxygen's nonsense and because of its inner strength is okay with this. So if you know anybody like that, fine. Yeah. And then you got hydrogen. Nobody wants hydrogen. Hydrogen is a thing that kind of it's around, but you're like it would always be just about as good if hydrogen wasn't there. It's almost nothing. So yeah. I don't know. We don't maybe have to make somebody hydrogen, but there are qualities we can admire or despise in each of these others. I think so. Fine. That just makes it easier to remember. That's all. Okay, so I've drawn our beautiful reaction mechanism, and I wrote up here in my very best, very bad handwriting, chymotrypsin. And so special areas of chymotrypsin. Oh my gosh, I left out an area. What the heck am I thinking? So we've got down here our specificity pocket, right there, yeah. And up here we've got our oxyanion holes. So let's see, we've got a couple of carbons, little hydrogens, and together these are the oxyanion hole. Nice. Okay, fine, excellent, in fact. So, basically, the way this starts out is that a protein walks into a club or bar or whatever you want it to be. This can be walking into Sunday school. It's just fine. You can make this work. Yeah, just whatever works best in your own version of the story, and whatever helps you remember it ultimately is the right answer. You don't ever have to tell anybody what helped you remember it. Unfortunately, I do. Yeah. So here we go. Yeah. So this is going to be our protein. And here we have our peptide bonds. This is the carbonyl carbon, and this is the little amino, nitrogen. And the R1 is going to be the front half of the protein, and the R2 is going to be the back half of the protein. So the protein's coming in this way, and this is the front. Yeah. So, first thing that happens when you go to the club, I mean, you know this, right? Yeah. I don't know this from actual experience, but I am told when one goes to the club, one must first get past security, like the bouncer. They have to check one's ID, for example. That's basically what the specificity pocket is doing in our little metaphor here. It is sitting here at the door, and if you have the right R1 group amino acid, then you can come into the club. And if you don't, then boom, you're bounced. Yeah, you're banned. You're out of here. Okay, so we're moving in here, fine, and so let's move this on up. We'll put R1 in the pocket. We'll put our little carbon with the double bonded oxygen here. I'm just going to bend the molecule a little bit, but all the connections are going to be the same. nitrogen with the hydrogen, and then R2 can hang out down here. Okay, same molecule, we just moved it over and bent it a little bit right there, which is fine. All right, so now we're trying to represent three-dimensional things on a two-dimensional board, and not completely accurately, just like accurately enough schematically so that you can understand them. Yeah. Hence the bending. Yeah. All right. So what happens next? So while R1 is being detained down here in the specificity pocket, the rest of the protein gets a look at the club. So it's like you're going with somebody and one person gets pulled aside, but everybody else kind of, gets to go in and see what's going on in the club. Yeah, I don't know. Imagine it happens. It only has to happen in this protease mechanism. Okay, now in the club, you can see these are your players that are in the club right now. You got your oxygen. Remember, oxygen. A little greedy, always looking for something else. Oxygen with an electron, you don't want to see oxygen with an electron. It's basically going to stab that electron into whatever is nearby, preferably carbon. Yeah. I don't know. Somebody should keep oxygen out of this club, and yet oxygen keeps getting in. I can't say why. Let's see. Over here, we've got nitrogen. Okay. And this one has a pair of little pocket electrons they can use to try to attract this hydrogen, which is actually bonded to the oxygen. And so those are stable right now. We got a hydrogen bond, and we got a second hydrogen bond going on down here. This oxygen with a negative charge can't quite reach and doesn't really want maybe this hydrogen, which is already bonded up here, and so it's fine. Actually, no, this hydrogen should be on the nitrogen. There we go. Sorry. There is a hydrogen there. That's not the one that's bonded. This is the one that's bonded. Oh my gosh. Yeah. What the heck? There we go. Okay. Better. We have fixed reality. Oh my gosh. Thank goodness. Okay. So, first thing that happens. Protein walks into a bar. Or a club. Whatever. Next thing that happens. It goes to the specificity pocket. Basically the bouncer. Yeah. Who says, let me check your ID, and all this is going to happen while that ID is being checked. R1 is going to be locked in this pocket for the entire reaction until it's over. So, next thing that happens is that oxygen has been waiting here, waiting in the club, sees brand new carbon walk in, and oxygen's like, oh my gosh, gotta have that. Yeah, because this is oxygen we're talking about. Oxygen, kind of a scumbag. Yeah, I don't know. maybe. And this doesn't have to be misogynistic. You can, these can be female characters if you want. Whatever works for you. So oxygen's going to go after. Well, first, oxygen is already bonded to two things, and oxygen can only have two bonds at a time. And so what oxygen does is it basically shakes off the hydrogen. It's like, go play over here. And so hydrogen is going to go play over here. Hydrogen is going to go over, and boom, there's our new hydrogen. All right, but the histidine over here, this histidine ring can hold one hydrogen at a time. It can't hold on to two of them, and so it's got to give up this hydrogen. But that's okay. It was already kind of leaning toward this oxygen anyway, and so this electron will become the bond, and bam, we've attached the hydrogen, and we're still hydrogen bonding. Nitrogen's looking back, and there we go. And now we have got oxygen with a negative charge. And here, we better draw this oxygen in red as well. Because it's an oxygen, and all oxygens are, pretty much the same thing. Alright. So, we got our oxygen with a negative charge. Great. Looking great, but it's got a -1. And so that's an oxyanion. An oxyanion is bad news because it's got to stab something right now. It's got to go after the nearest carbon, usually, that it's not already bonded to. And so it's going to look at this thing and say, yes, fresh meat, let's go. And so oxygen is going to make a bond, and I'm making this bond a little bit longer than it should be, just because I've drawn it a little bit less accurately than I should have drawn it. Yeah. Now, what we got here, oxygen is now satisfied. It's made a bond with a carbon. That's all it wanted to do. That's all it was looking for. Carbon, though, carbon is all about having 4 bonds. Not 3, not 5, 4 bonds. And look, we got 1, 2, 3, 4, 5. Oh no. Carbon is not happy, and so carbon has to get rid of one of the bonds. It just has to. It's like the accountant, if you like. It's got to be 4. 4 is its number. And so we're going to push one of these electrons up here. Temporarily. The reason why we can do this is because here we have the oxyanion hole. And it's just in the right position in 3 dimensions that it can stabilize a negative oxygen with a negative charge, an oxyanion, for just a minute. And so that's what allows this to be the bond that breaks and makes a negative charge up here. And so we're going to have a temporary little attraction to the oxyanion hole. Now, as far as I'm concerned, the oxyanion hole is like the part of the club, and again, I'm getting all my information from rap videos, but the part of the club where there's champagne and there's like a velvet rope to keep people like me out. Yeah. But oxygen gets to go back there. So it's lost one of its bonds to carbon, but it can soothe itself temporarily in the VIP lounge. Yeah. So good for oxygen. Oxygen, don't ever worry about oxygen. It's always going to be fine. Okay. Carbon satisfied, oxygen satisfied. Everybody's satisfied except that this oxygen still has an electron. And if it has an electron, it just needs to stab it into something. Yeah, because it's oxygen, baby. That's what it is. So here's our oxygen. It's going to come back down. And even though it just went up here briefly, that's what allowed it to get to this state, which is called the tetrahedral intermediate. Now it's got that negative charge and it's going to come back down and it's actually going to, boom, stab it back into the carbon. And so now, once again, carbon is going to end up with a problem. It's going to have 5 bonds. And this oxygen is the one that just did the stabbing, so it can't be giving its electron back. It's doing the stabbing right now. And so basically, the question is, which is the weak link? Which is our little peacemaker here? And of course, you know, I know, nitrogen knows. It's nitrogen. Yeah. So yeah, let's make our nitrogen blue. There we go. So they're all the same color. All right. And so to resolve this problem of carbon having 5 bonds when it can only have 4, no more, nitrogen is going to take back its electron. So it'll have a little negative charge. It's then going to take this hydrogen from up here. That's going to go down, and it's going to make a little bond. And so we have now got, and when that happens, this hydrogen, it gets yo-yoed back and forth. It's going to end up back over here. So we got an oxygen with a negative charge. Still looking at that one. And now look, the second half of the protein, the R2 half, is now free. It's not bonded to anything. And so, if it's free, it can exit the club. Boom. Yeah. And it does. So there we go. First half of our protein exits the club. All right. Now, we got a problem. Because look, your serine is supposed to have CH2 in the middle and OH at the bottom, not O and an entire rest of the protein attached to it. We have ruined our serine protease. And if this actually happened in the real world and stayed this way, you could break a protein exactly once with a serine protease, and then it would be ruined, and you would have to make another one to break it a second time. It would be very inefficient, and we would be dead. Yeah, so thankfully it doesn't just stop here. So the next step in our little weird play is going to be that another molecule is going to enter. And you can think of this molecule as a hero because it's going to resolve the problems, or you can think of this as just another oxygen because it kind of is. Yeah. So we got an oxygen up here, and oxygen does not just roll into the club on its own. Oxygen always has an entourage. And so here we're going to have H and H. That is H2O. That is water rolling into the club. Yeah. Water is a VIP. It just goes right past that bouncer. It does not have to stop. Yeah. Gold card or whatever. Again, yeah. No understanding of the real world here. Just, just movies and things. All right, so let's move this up. Let's get it into position. Okay. O with an H and an H, something like that. All right. Now oxygen does what oxygen always does. Oxygen sees something a little better than what it has. And oxygen goes out and gets it. So yeah, that's the positive spin. Yeah. The negative spin is oxygen's always dissatisfied and wants more. So oxygen is going to throw away this hydrogen because who needs that? It's going to take the electron though because it would rather not share that. And so hydrogen is going to go up here and hang out. So one up here. And we'll erase those little dotted lines because now it's there. All right. Now, with its little negative electron, what is oxygen going to do? What does oxygen always do? It always finds a carbon and sticks it in. All right. So oxygen's got a carbon here, and bam! Done! Yeah, success. Except that, oh no, look at carbon. Carbon now has 1, 2, 3, 4, 5 bonds. Carbon cannot have 5 bonds. Yeah. We've been over this carbon. Yeah, it cannot be. And so, same thing happens as before. We decide which one leaves because there is the oxyanion hole, the lure of the champagne lounge up here at the top. And so temporarily, this oxygen, with its little negative charge, with its extra electron, is going to hang out for just a minute in the oxyanion hole. And then, oh, it's coming back. It's going to be back on the floor just in a second. Yeah. All right, so carbon's happy. We've got 4 bonds. Weirdly, 3 of them are oxygen. Yeah, this poor carbon. Yeah, I don't think it ever wanted this many oxygens around, but it's got them. Yeah. Let's see. And now our oxygen with a negative charge is going to come back out of the oxyanion hole, and it's going to stab that right back down. So we're going to, boom, make that bond again. We just made this one, so we can't break these guys. And we, that's just an oxygen trying to hold on to one atom, so that's pretty easy. That's carbon sharing equally with another carbon down in the chain, so that's happy, no problems there. And so the weak link is actually, look, this guy. It's an oxygen, and he's got it all right now. Or she's got it all, or it's got it all right now. It's got 2 carbons of its very own. Can't hold on to 2 carbons at the same time. Can't be done. Can't be done. I mean, it can, but it's a real unstable position. So this is what happens. This oxygen loses that bond, but gets back its electron, because oxygen's not going to give up the electron. Yeah, unless you, pin it down and beat it up, basically. And now, look. The second half of the protein, the front half, is now free. It is no longer joined up to the protease, and so it can leave. It will exit our little weird little play here. And boom, it's gone. Gone. Meanwhile, oxygen with a negative charge and a bad attitude, looking around, can't quite reach either of these guys or that guy to stab, and so, I don't know, I feel like reluctantly, just because it's the only thing left, oxygen is going to take the hydrogen back. It's like, fine, it's better than nothing. So, O, H. The hydrogen, though, is still looking over here, saying, I used to be over there. And likewise, our little hydrogen is back here, but it's still looking over here at this oxyanion, and that's the entire mechanism. So normally in class, I would then do this again. Yeah. And then I would have you guys do it on paper. And then I would have you do it on paper again for homework. Yeah. But since we're online, you're going to just watch this video again. And then watch this video and pause it and try and predict exactly what's going to happen right before I do it each time. And then make the starting setup from this video and sketch it out. You can do it with the video maybe the first time, and then the second time, try and do it with just the starting setup and you mentally going through the steps and remembering what has to happen. Because, here, let's move over. Oxygen, carbon, nitrogen, hydrogen, they're only going to do the one thing that they can do. And this actually gets you a lot of organic chemistry. If you can personify these things correctly, kind of the way we've done, a lot of reaction mechanisms will just all of a sudden make sense. And yeah, you basically got it. You got biochemistry, bam, right there, and a little organic. So there we go. That's where this ends. Yeah. So watch it again. Keep watching it. This is going to be totally guaranteed on your test. I'm not sure if you're going to have the first half or the second half. Nobody knows that because I haven't randomized the tests yet. But you're going to have one or the other, that's for sure. And if you have one bit, somebody else is going to have the other bit. So learn it, memorize it, get it done. Get it done. All right. Thanks very much. Bye-bye.